we're going to do, again, is look at the three objectives. First, we're going to talk about how force affects the motion of an object. And we're going to differentiate between what's called a contact and a field force. And then we're going to take a look at free body diagrams. Has anyone heard that term before? Free body diagram? Okay, so it's new. Good. It's not a big deal. We call those FBDs. FBDs. And we'll use the abbreviation in a moment. Let's take a look at the first slide. First, the thing that causes acceleration, as you all saw from your introductory lab a moment ago, is force. Force is what causes acceleration. When you had no force acting on the object, suddenly what happened to the acceleration? Yeah, it became zero. The object was still moving, remember? Because we didn't have friction on in the beginning. So even when you apply a force to this garbage can, and I push the garbage can, and I let go, without friction, that object will move on forever. But there won't be any more acceleration once I let go. So a force is really just the cause of acceleration. Okay, it's not the definition you're going to see in your books and stuff, but this is what I put down because it makes more sense. Okay, it's what causes acceleration. That's how you remember force. Now, generally, forces are described as pushes and pulls. A push and a pull. Just like when you look at magnets, we're going to look at this year. The magnetic force can be a pull or a push. If you have two north poles, they push apart. If you have a north and a south pole, they pull together. Okay, attraction and repulsion. So you have a push or a pull with forces generally. The measurement of forces is newtons, named after Isaac Newton. Okay, named after not the figs. Named after Isaac Newton. Now, a newton, just so you know, is a kilogram meter per second squared. Everybody see that hyphen there? That hyphen is not a subtraction symbol. When you see a hyphen with units, it actually means times, which I know is a little bit misleading. And by a little bit misleading, I mean a lot misleading. Okay? So again, the units of newtons are kilogram times meter over second squared. But in your book, you're going to see this with a hyphen. So I want to make sure we clear that up. There's not a minus symbol. When you see a hyphen in units, it means multiplication, actually.
And why is that like that?
You know, that's a really good question. I don't know the answer to that.
Is that just to prevent people from being able to do this?
No, I mean, to me, honestly, I would do it this way if it were me. Okay? That's how I would write it. I write each of my individuals like that, but it doesn't matter. I don't know why the adoption was made where units with the hyphen was considered to be multiplication. Maybe you can look it up and tell us. It's a good question. That'd be like a history of physics thing. I don't know that one there. Yeah, Joey. So the numerator's units are not kilograms, they're not meters, they're the product of kilograms and meters.
What?
You'll see in a moment when we come up with our formula.
Why have we never seen that before?
Because we haven't had that opportunity yet to see that. Okay? But give me a minute and we'll see that, okay? I'll show you once we get to our formula. We'll be able to notice it. Let's see. All right, now, what is acceleration defined as again? What is acceleration defined as?
The rate of change of velocity.
Perfect. Very good, Joey. The rate of change of velocity. So, if a force causes an acceleration, but acceleration is defined as a change in velocity, then we could say that a force causes what, really? Use the transitive property, the chain rule. If a force causes an acceleration, but an acceleration is really a change in velocity, then
Force is the change of velocity.
a force causes a change in velocity. Okay? That is the transitive property. Transitive property of equality. Okay? I think it's law of syllogism in logic, I think it's termed, where if A implies B and B implies C, then A implies C.
Yeah.
The idea, though, again, is that because force causes acceleration, well, acceleration is change in velocity, so a force causes a change in velocity. So what does that mean? If there's no force, the velocity is?
Zero. Or constant.
Or constant. It could be zero. Let's write that down. If there's no force, then there's no acceleration, so there's no change in velocity. So no force means that the velocity isn't changing, or the velocity is constant. Okay, so when F equals 0, there is constant velocity. When the overall force on an object is 0, the velocity is constant. Here's a good example of that for you. So, it's the winter time, and you decide to use a sled or a sleigh in the snow, and you're pulling your younger brother or sister who's only a baby, for example. So you're pulling them quite slowly, right? You're not going to be like whipping them around for like 2 years old. One would hope. Now, initially, the baby is sitting in the sled or sleigh at rest, and you start to pull. You notice in the beginning you have to kind of get it going, right? You have to overcome that friction force that it's sitting in. So you have to pull initially to start. But once you get it going and you start moving like this, what do you notice? If you're moving at a constant velocity, what is there a balance of? What is balanced when you're moving at a constant velocity? Because now there is friction. In the lab we didn't have friction in the beginning, but what's balanced now?
The force that you're applying, that you're pulling with the sled,
Is balanced with what?
with now the velocity that you're running at.
It's not balanced with the velocity, be careful. If I'm moving and I start pulling on this sled, watch me, I'm going to use the chair, okay? And I'm pulling at a constant velocity, and I'm not increasing my velocity, what is balanced right now?
The force of which you pull the object and the weight of the object.
Not the weight.
Velocity that you're walking at and the velocity of the sled.
They're the same, but that's not what I asked. I said what is balanced. That is true. That is true, but it's not what we're looking for. Julie?
The applied force and the mass.
Not the mass. You're all right by saying the applied force. You said the weight. You said the mass. They're different things, but they're both not right actually right now.
Well, if you're pulling it up, is it balanced with the friction?
Perfect. The friction. Why? What wants to slow you down, people?
Friction.
Friction always wants to. The snow, sure. The friction. So if you can maintain a constant velocity, that means that there's no overall force acting on the object. Okay? Again, when there's no overall force acting on an object, it means there's no acceleration, which means that either it's moving at a constant velocity or it's just sitting still. Okay? So there's a good notes to write down here. These are the kind of things that will guaranteed end up being a multiple choice. Okay, these kinds of questions. That's why I tell you to write these things down as we go through them. It's a balance between the force applied and the frictional force. Okay? When there's no force acting on an object, when there's no net force, okay, it's a balance. Because right now, look, if I start running and I pull this fast enough, the force I'm pulling at exceeds the friction force, which is why I started accelerating. But the minute I start moving at a constant velocity, the friction force and the force applied is the same. They balance each other out, making it a net force of 0. Okay? And we'll talk about that in a minute when we look at our FPVs. Let's take a look at the difference between contact and field force. It's pretty obvious when you look at the definitions. Give me other examples besides what you see on here. Contact force, a force that comes from physical contact between two objects. A field force is one that exists at a distance. Okay, if you don't want to use the word contact in its definition, you could say from the physical interaction between two objects. Okay, if you don't want to use the word contact, you can say interaction. What is another example of one or both of these that you've seen before? There's so many examples of contact force. You can just list a million of them. But field force is limited. Give me examples of either of them. Either of them. Lisa.
Field force, like pouring cereal into the bowl.
Yes and no. You need to give more detail about that. I can make that work if I tweak your words a little bit, but how can you make it work yourself?
I don't know.
Okay, let's come back. We'll come back to it. James?
You want an example of field force? Like magnetism?
Magnetism, good. So the first thing for field force, an example, would be magnetism. What would the force that Lisa was speaking about a moment ago be called? That causes your cereal to go into the bowl?
Contact.
Gravity. Guys, when you pour your cereal out of the box, what caused it to fall into the bowl is gravity. So if you were speaking about that, you're right, but I didn't hear that. That's why I was saying that. So an example of a field force would be gravity. Does gravity occur only when I'm in contact with the ground? No. If I jump in the air, Even when I'm up in the air, gravity is doing what? Pulling me down. So gravity acts at a distance between objects. The magnetic force, as James said a moment ago, magnets pull at a distance. There are electrical field forces. This is what? What are you noticing here? It's a balloon and paper. Anybody know how the paper is able to be pulled up by the balloon? Static what?
Electricity.
Yeah, static electricity. Okay, also a field force.
So, and like you take a balloon, run around your head, and it's moving up.
Because you're charging the balloon with electrons, imbalance with it, pulls it up there. Very good, very good. Contact forces. What are some contact forces examples?
Geo gets slapped.
What are some contact forces? Stop it, Tristan. What are some contact forces?
Baseball.
Hit. Yes, obviously. Thank you, Lisa. What else? Julie.
Loose baseball bat hitting Geo.
Loose big, that's not very nice. What else?
Swift.
What if you deserved it?
Leave Gio alone. Jeez.
High-five someone.
When you high five someone, good. You high five someone, there's contact. You can feel the actual force. Okay? You can feel that force occurring. What else? Besides stuff that you do, besides contact forces that you do or that you create, where do you see other contact forces all around you? In a car, give me an example.
The engine and brakes or something.
Yeah, perfect. The engine and the brakes. The engine applies a force which pushes the car forward. It gets the axles turning, the wheels push off with rolling friction, causing the car to move forward. Then, that friction helps you with the car, by the way. It helps you move. The friction between the tire and the road. Then, the brake does the same thing. The brake pads, they put pressure on the tire, causing the tire's rotation to diminish or to slow down. So the brake is a contact force. There's contact. What happens to your brake pads over time? They wear out because there's contact. So they start to disintegrate in a sense. And eventually you have to get them replaced because of that contact.
It's like a pencil after you use it for a little bit.
Yeah, exactly. A pencil, in order to see a line on the paper, if you just go like this with your pencil, very lightly, you're not going to barely see anything. But if you push down, what happens?
Contact force.
Yeah, the contact force increases. A lot more of that graphite rubs off onto the paper, and you see a darker line or a thicker line or whatever it is, okay, depending on what you're writing with. Okay, so contact force versus field force. Next, we want to look at free body diagrams. Now, a free body diagram, okay, it's a type of force diagram that we're going to look at. And generally, it shows all the forces acting on a single object, okay, that affect the motion of that object. So here's what I want you to do. Draw a box on the page, maybe like this big, okay, to represent an object. Now, what I also want you to do is to think about for a moment an object like a train, okay? Think about a train and think about a train that is accelerating to the right. That is accelerating to the right. And list, you don't have to draw it on the diagram yet, but on the side, list all the things as far as forces that would be affecting it. What would be affecting a train that is accelerating to the right? What kind of forces? And just list them on your paper. You don't have to draw it on the diagram. We're going to label the box in a minute. Just leave the box. The box is going to be our diagram. But just list the forces on the side.
Wait, I'm sorry. What do we, draw lines?
With air resistance? I think so.
Again, people, you're just listing stuff. A train is accelerating that way. What forces are affecting the train? Give me one. Give me one, Nick. Friction. Now, remember that friction can technically help or hurt moving objects, believe it or not. That's how a wheel is able to work. A wheel works because friction exists. Okay, moving you forward. If you're on a bike, every time you pedal, the rubber pushes off the tire, pushes off the ground, pushes you forward. So friction helps you there, or on a train, if you're coming to rest, friction doesn't help you. It helps you stop, really, but it doesn't help your motion. Okay? So friction, what else?
If there was no friction with the tire, just like move but not spin.
So like, if there was no friction at all, and I went to roll this like this, it wouldn't roll, it would just do this.
That's a tire.
It would slide forever. Okay? Things would not roll if there was not friction. They would just slide. So the wheel is only invented because of friction. Okay? Again, I'm telling you guys, Ender's Game. Read that book. So good. I'm at the very end of the first book right now, the series, and all this kind of stuff that we talk about is involved in it. Maybe wait until we do momentum and then read the book.
You watch the movie?
If a lot of us, if enough people read the book and we want to, sure.
So the wheel will just turn into. Can you take us to the movie
What's that?
theater? So the wheel will just turn into the movie theater.
If you, it depends on the scenario how you get it started. But if you had a wheel on an axle and you just tapped it, it would spin forever and ever and ever without friction. Okay. What else? What other forces are acting on this train that is currently accelerating to the right? Accelerating to the right. Remember, that's what I said a moment ago, that acceleration is directed to the right. Nina.
Wind.
What is it?
Wind.
The wind. So air resistance.
Cargo.
Wind.
Air resistance. What else? What else? Tristan.
Cargo.
What do you mean cargo? All right. Let's hold off on that. But what holds you to the ground? Not your mass, but your.
Gravity.
So let's say the gravitational force or your weight.
But you're on the ground.
Okay. Your weight is what holds you to the ground. Your weight is pulling down with 150 pounds or 160 pounds or 190 pounds, whatever it is, holding you down to the ground.
Wait, what if you had zero weight? Would you like fly?
You can only have zero weight if there's no gravity. But on Earth, there's gravity. In space, what happens? No gravity, you float. Okay? Good question. What else? What else is affecting this?
The state of the wheels. Like maybe they're rusty and they
So more friction. Good. But it's still lumped into friction. Good point. Rust between the wheels. Any sort of heat loss in the gears moving. Still listed under friction.
Would there ever be any way to have an environment that has no friction? Like,
No, not
We can create
a vacuum. Sorry, a vacuum when there's no medium is frictionless.
So if you spun a wheel in a vacuum, it would spin forever.
Yeah, technically. Let me think about that for a second.
So why don't we make infinite energy?
Well, no, the problem with that would be that gravity is pulling you down. So over time it would come to rest. And you couldn't create endless energy like that because you would have to have some sort of force that you're driving. You would need a driving force to do that. Solenoids are the closest thing to that. When we get to electrical stuff, we'll talk about solenoids. And those have to do with like the magnets and the magnets causing the object to spin. And that's an energy generator.
Oh, like the video you showed us? No? The cool one that you posted?
Yes, with the object perpetual motion, yeah. Yep. There's something else though, people. Guys, look for a second. Everybody look at the board. Friction, in this case, for the train is slowing you down. Air resistance is slowing you down. The weight is pulling you down to the ground. Something's got to be helping us. How are we moving to the right? What can we call that? A driving force or an applied force. Now, there's also something else, and we'll talk about this in a little while, but there's something else that's also pushing us back from the ground. And what's called the normal force, but for now, we could say like a reaction force from the ground. Okay? So, here's what I want to do now. The box is our train. Okay, the box is our train. How would I draw weight if I were to draw it using a diagram? How would I draw the direction of weight? Which way does weight pull you, Tori? Down. And weight generally acts from the center of your body. We call it the center of mass. So we draw that from the center of the box, acting down. And we label that Fg. And we'll talk more about this in the next section, which means the force due to gravity. Okay? Some books call it capital W. The reason I don't is because capital W represents work, It also represents wattage for watts. So later on, we're going to see capital W and other means. So whenever I refer to forces, I'm going to use a subscript. Is everybody clear? The G is a subscript. It is not a variable. Fg together is one variable. Fg is the force of gravity. It's your weight. It's one variable. G is just a subscript.
I'm a lab, but
Yeah, this is weight, yeah.
in the program,
Really?
in the lab,
Nobody?
It was like a diagram. And it was kind of like that. I think it's maybe what we're drawing. Yeah.
Yep. That's exactly what you're drawing now. In the upper right portion of your lab, there was a free body diagram which showed the forces acting on the object. And a lot of you noticed there was weight acting down and then something pushing back up. What's pushing back up is this ground reactive force we're going to call the normal force. And the way we draw that is from the bottom of the box upward, like this. From the bottom where it contacts the floor upward. And we call that Fn, okay, which is the normal force. We're going to go over these again in the next section, okay? In 4.2, we're going to talk about the types of forces. But just to give you an example for your free body diagram. So those two things keep this object from floating pretty much. Right? I'm pushing down on the ground, but what's the ground doing? If the ground couldn't push back up, what would happen to me? I would fall through the ground, and I would go right through the ceiling and into the next floor. But thankfully, I don't weigh too much, or the force is strong enough to hold me on the floor. Okay, so my weight does not exceed the yield strength of the floor. When the floor, its yield strength is exceeded, it will break, and you will fall right through. Okay? So right now, the floor is able to hold me up because the normal force is equal and opposite my gravitational force. What about left and right? What's slowing down the object again here? What's slowing it down?
Friction.
Friction or air resistance. So let's draw for this case. We always draw it from the ground. FF, force of friction. Okay? Fn is the normal force, which is the same as the ground react. I can hear almost everything that's said. The ground reactive force is what the ground is pushing back up with. We call that the normal force. And I'll explain why it's called the normal force in the next section. For now, just write it down, okay? The force of friction, although it's not just acting between object and the ground, take a look here. If I slide this water bottle across the table, friction is acting between the table and the object, which is why we draw FF on the bottom of the object. Although air resistance is actually everywhere on the object, right? Okay, if you're running, where is air resistance resisting you? Everywhere. Not like just pushing you here or here or here. It's pushing against your body everywhere it made contact with. Okay? So air resistance always acts against motion. So what's pushing to the right? What's the last part? What's the last part?
Applied force.
The applied force. We're going to use FP for push or pull, but FA would work as well, and that usually is drawn from the center outward. Now, technically, I could draw this force on the other side as long as I draw it still pushing to the right as a push. This would be considered like a pull, right? If I were to go like this in the chair, everybody take a look out front. Here's the chair. Oh, let me draw it, or let me set it up so I'm analogous. And I went like this. What am I doing to the chair? I'm pulling it, right? If I went behind the chair, though, like this, and went like this, now I'm pushing it. But it has the same effect, doesn't it? So FP could be drawn on the right side, or FP could be drawn on the left side over here, and I'll draw it with a dash. Okay, FP could be over here also. Either way, as long as it's pushing it to the right. Well, that's the question now. What's pushing the train? Energy, which is causing the gears to turn. The gears turning are causing the friction between the actual roller at the bottom, which is like the wheel, okay, that's pushing it or propelling it forward. And that's continuing to move. Now, once a train is going at a fast enough speed, it also uses its momentum, or the inertia effect, to keep it moving. Okay? So it's not always going to be that. But what's applying in FP is the actual motor, which is pushing it forward. Traditionally, you call this maybe like a thrust force, because on a rocket ship, when you have an object on a rocket ship propelling out the bottom. So for example, when a rocket ship takes off, you see the fire come out the bottom. Ever see that before? When you see like a space launch, you see all the smoke and all the fire out the bottom. That's pushing down. When that pushes down, that causes the object to move up. And we'll talk about that as one of Newton's laws, okay? We'll talk about that in Newton's laws. Tristan.
There was this video where it was like a rocket propeller, but it was water. And this guy was in the lake and there was like a scoop coming out of it.
That was on one of the videos I put on the newsfeed, yeah. So you're talking about the guy where the guy was like hovering in the air, right? So there's these new things called like, it's called like water hover or water
Yeah, I've seen those.
something.
I've seen with the people in person.
They do what?
I've seen like the person doing that.
You've actually seen a person doing it? Yeah. So they have this like jetpack, and the propulsion of the water coming out the bottom of the jetpack is equal and opposite the force of gravity, and they can actually hover like in a rocket, like in a jetpack, like you would use like normally. But where's the water coming from? It's coming from the ocean. So there's tubes into the ocean which fill that and use a compressor. The compressor pushes the water out the bottom of the jetpack. The jetpack then pushes them back up, and it holds them in space, and you can kind of float in air. It's pretty cool. Probably costs a lot of money to use it right now, but
They're like boards, it's like a snowboard.
it's like a hoverboard or a hovercraft. Yeah.
Yeah, you just stand on
It's the same thing as a hovercraft would be. Anybody ever see Back to the Future?
Yeah.
Remember when he has the hoverboard in the future?
Yeah.
And it's like using the hoverboard? It's completely not right. Sorry to ruin your physics statement, but it's not right one bit. You need some sort of propulsion device on the bottom to counteract the gravity that's on it. Okay, you can't just like, oh, it's a hoverboard, let me get it how it works.
That's heavy.
What?
That's heavy.
That's heavy? Heavy, get it? Yeah, heavy. Yeah. I like it. Why is everything so heavy? Has the gravitational force changed in the future? That's what Doc says. He does that. Alright, so what I want you to do in the next 5 minutes is draw me a free body diagram of the following scenario. All I want you to do is draw me a free body diagram of the following. Let's say an object is being pulled by a rope that's connected to it. So I attach a rope to this chair, okay? And I pull on the rope at an angle. So here's the chair. And I'm going to draw it as a chair, not as a free body diagram. Obviously my art skills are not really there, but there's the chair. Okay? Pretty sweet chair. Now, there's a rope attached to the chair. And there's a person over here. Aaron, it's going to be you. Okay? So Aaron is pulling on the rope. Aaron, we'll give you some blonde hair. Okay? So Aaron is pulling on this rope, and let's say actually, let's do this real quick.
The chair just falls.
Let's make Erin a little bit taller so she can pull from above. So let's can I slide this up and down, or is this going to work? No, it all moves together.
You could take off the top of the chair and make it lower and then...
Yeah, let's do that. Let's make the chair a little bit smaller. Make the connection point here. Okay?
Wait, yeah, what
It's just gonna...
Now, I know the chair might topple over, I know, because of its moment of inertia. The chair could topple over. Let's imagine the chair doesn't topple over, though, please.
but then wouldn't that apply to this definition?
Okay? So look, I attach a rope to the top of this chair, okay? And I start to pull on it, even if it's this way, okay? The chair starts to move this way with me, so I'm pulling at an angle. So what I want you to do is draw a free body diagram of the chair. Draw a free body diagram of the chair alone. Okay, remembering that a free body diagram is all the forces acting directly on the chair. Directly, that's the key word here. Okay, what is directly acting on the chair? And it might be a little bit misleading the first time you draw your answer, and you might be wrong the first time, which is okay. But we'll correct it. So list and draw the forces that are acting directly on the chair. Remember to draw the chair as a box in space. So here's your free body diagram beginning right here.
Wait, is this
I'll give you the first start. No, it's right now.
That's right. This said homework on top.
No, the homework is what you're going to do tonight, but this is just right now.
There.
So here's the chair right here. Draw all the forces acting on the chair. Draw all the forces acting on the chair.
Should we assume the chair is like on like regular drag?
Sure. And label those forces, please, as you go through this.
does everything have the same voltage?
I want to see what you come up with, and then we'll go over it. But I want you to draw them. Please draw them on the diagram.
That's a good time.
Tristan,
Yeah.
stop talking and go through this. Gio, stop instigating. Come on. So what's pulling the chair to the ground?
Force of gravity.
Good, the weight or the force of gravity.
There's still force in that.
The ground is indeed resisting it still, right? Next. Friction. Friction is still acting which way? Okay, it's opposing the motion. So we'll see that there's really not much difference so far. What about this last part though? How do I draw this last part?
The force, you're getting to the right hand.
Yeah, so we need to draw it like this. Remember, I tried to emphasize this a moment ago. The chair is being pulled at an angle, and that's what I was saying. So the chair is here, but the rope is up here. So the rope is at some sort of an angle. If you look at the diagram, you can see that the rope is at an angle with the horizontal. Okay? So that force of pull needs to be at an angle now. Now, notice, you're not drawing Erin in the picture. You're not drawing you're not saying like the pull of her arm. You're saying what's acting directly on this object. Normal force is up, gravity's down, friction's left, and the pull coming from the rope is to the right. If instead of writing FP, you wrote the following, believe it or not, it is right. Instead of writing FP, you could write FT. Anybody have any idea what T stands for?
Tug.
Has to do with a rope.
Torque.
Tug makes sense, but it's not tug. But tug doesn't make sense.
Torque. Temperature.
If you pull on something, it has what in it?
Tempest. No.
What is it?
Tension.
Tension. So, technically speaking, okay, Erin is applying a force of pull to the rope. The rope is now in tension. Guys, stop. The rope is now in tension. The tension from the rope is what's pulling on the object. So you could have labeled this FT or FP. Either one. Is that clear? And you're going to see that throughout this section, that we're going to have some ambiguity here and there. And we have to discuss what's actually happening. Julie.
For the force coming from the ground in reaction,
Yep.
what did you rule as?
Fn, the normal force. And we'll talk, guys, we're going to talk more about some of these forces tomorrow when we go over Newton's laws. This was just more of an intro, okay, to see what we do with forces.
Is FT or FP, is that going to really matter? Or
In this part, it doesn't matter, no. It makes no difference because they'd be the same.
but
There's only one rope. If there's more than one rope and the scenarios, different things can change, Jack. Okay? Make sure you guys work on your homework tonight. Take a look. There's only 3 problems. They're very conceptual. I think one of them you have to draw a free body diagram. The other 2 is just answering in words. Should only take you like 10, maybe 15 minutes max. You should also work on finishing up all the simulations from that lab tonight. At one point in the lab, it's going to tell you to change to Jupiter. You got to go to the bottom right, scroll down, and hit more controls to change it to Jupiter. Don't do it because you can't find it. It's under more controls. It says it there. Okay? Tomorrow, ask me questions about the lab. I'll let you know when it's due. It won't be due tomorrow, though. Okay? Please work on it tonight.